called behavioral modeling, which we'll talk in a bit more depth in a moment. Before we get started, I'll go over the agenda. I do want to talk a little bit about NextRev, who we are, and some of our power hours and training courses that we offer. And then we'll move on to a little bit about the behavioral modeling and product optimization. So NextRev has been working with PTC products for about 12 years now. We are headquartered in Santa Clara and do handle everything that PTC offers, from Pro Engineer to Creo Parametric now, as well as Creo Elements Direct, Creo Direct, and the Windchill products. So our weekly power hours, if you're joining us today, you obviously know that we do offer these weekly. However, maybe you're wondering about what happened last week or last year for that matter. We are currently in the process of uploading all of our old power hours, so you will be able to go back in time, as it were, and see a little bit about what's offered in maybe what we had in Wildfire 5 or Creo Parametric 1.0. So you are going to have the ability to actually go back and see these old power hours. As you can see, we are going to be having a few more coming up, including working with Model Check, introducing PDM Essentials, and even working with mechanisms. So please do check out our future power hours. We'd love to have you there. We do also offer courses not only at our Santa Clara facility, but also in Southern California and the Pacific Northwest. I do want to let you know as well, though, that despite the fact that we offer training at our facilities, we can also come to your location and offer both the standard training classes and maybe something that's a little bit more tailored to your company's needs. On the West Coast, it does handle Creo Elements Direct, which is formerly Co-Create, as well as Creo Direct. If something is not shown on our website for training, that does not mean that we're not offering it right now. Please let us know if you have any questions, and we can always set up a training class on the fly for you and your company. Before I get started, I just want to let you know that at any point, if there are any questions or if there are any problems with the audio, please type them into the question box here to the right in GoToMeeting, and I will definitely check those out, especially if there is going to be some sort of audio problem or video problem. So moving on to behavioral modeling. Some of the benefits of using this tool to help optimize your designs is that you're going to be able to actually take your requirements and embed them into the part design process. This is going to allow you to better understand the effects of changes on not only one feature, but multiple features at the same time. Ultimately, this is also going to allow you to export these to external applications, such as outside tools like maybe ANSYS, but also to internal tools such as Flow EFD or even Creo Simulate, formerly Mechanica. This is going to allow you the ability to actually consider multiple design changes in order to produce an optimal part. And on top of that, this will give you the ability to use to run experimental studies on your features to give you maybe a variety of different results. The beauty, of course, this is going to do all the changing calculations on the fly, using different goals to actually point to. Well, without further ado, I do want to move on to the demonstration. I did leave the introduction a bit on the lean side, as at the end I am going to cover everything that we talked about to kind of reiterate what we did, and there may be some questions as well. So let's just move on to the demonstration, and then we will open it up for Q&A. So I'm in Creo Parametric 2.0 right now. And I'm going to give you a bit of a scenario. So this is a fluid container. Maybe it's for a car washer bottle, coolant overflow tank. Needless to say, we have a design requirement that we have to have 7 liters of fluid in here. Now I have already run a design analysis on this here, bottle volume, which is just telling us what the volume of the solid was. You can see that the analysis exists prior to us shelling it. Now we're not seeing any kind of value, so we can do that. Note that we always can add additional columns under our model tree. I'm going to do that for you. In fact, right now I can go under tree columns. Actually, can come in here and under feature parameters, we can type in a parameter that we've created, and it will show us the results displayed. Now I've done this to save some time already, so let's just open a settings file. What we're going to see here is the volume of the fluid, and this is in millimeters cubed, so it's actually 8 liters of fluid. Now that we've shelled this part, what I want to do is actually come in here and see what the volume of the current solid is. It is not a surface. This actually does have a defined thickness over here. Let's see that. And what we're going to do is go under analysis. Now again, this is an optional module. However, a lot of what we're going to cover does exist in all packages of Creo Parametric. So under measure, I can actually go to volume. Of course, I can just click on measure as well and open up the measure summary tool. It's a little bit more familiar so we can see it. When I open this up, I'll just select volume. And now it's going to default to the volume of the bottle. Of course, it's the only part here, so it's the only thing that we can actually apply volume to. And we can see that the entire volume of the solid model is about 0.25 liters. The thing is, when we fill something with fluid, we're not going to fill the entire thing with fluid. Just think about a soda bottle or a jug of coolant. You don't have the tip area full of fluid, so what we can do is actually specify a plane to chop off the measure. So we're going to click on selected plane, and we are going to select datum 4. So what's happening is it's now going to give us the volume of the solid in the direction that the plane's looking. So obviously that's backwards. We actually want to have this side as the volume, and we can see in this area here that the volume does change depending on which way the plane is facing. So I want it to face in that direction. Now what I do have to do is actually save this as a feature. So under the save, I can select make feature, and I'm going to call this shell volume. Now I want to actually make it very clear that this name is important because I'm going to reference it later. Okay, so shell volume, and we have completed that feature. Now just as a side note, I have a column here called one side volume, 1_side_VOL. I'll show you where that's coming from. Let's edit the definition of the bottle volume. First off, we can see that we do in fact have the datum plane pointing downward, but under feature, we have our parameters, and I've created a parameter called 1_side_VOL. And hence, that is why our numeric value over here, our calculation, is showing up under that column. So let's see why shell is not appearing. Same basic thing here. We have our analysis, but under feature, we also have our parameters. We can see that it defaults to something different. Now, I just want to keep things consistent. If you want to leave the default, then by all means do so. But either way, we must keep this consistent. I'm going to complete that. And now under our column, we do see that we can see the volume of the shell. Now at this point, we have to create an analysis. I want to see what the difference between this volume and this volume is, which is going to give us the internal volume of the container. This is not hard math, so let's just create an analysis. First things first, I want to make it a relation. This is going to be our equation, and let's give it a name. Let's call it a relation volume. There is relation volume. You must hit enter, otherwise it doesn't actually specify the name, and now we're going to click on next. But here is where I want to take things kind of slowly. First off, I want to create a parameter. That parameter is going to be called fluid volume. So there is my parameter. Now, of course, I need to figure out what the one side volume is of the of the bottle minus the one side volume of the shell. Mind you, I'm saying that one side again because that is the type of analysis that it was. Let's start typing in our equation. So one side VOL, and again, it's one side VOL because that is what we told it to be. Now I have to reference something which is the feature ID, so that's FID, that is consistent throughout Creo parametric. Feature ID of bottle, underscore VOTTE, then volume, and bottom bottle volume is this feature over here, and the model tree to the left. That's where these names are coming from. Now minus, we all know that one. And then once again, I'm just going to copy and paste this to save some time. I'm going to say one side vol, feature ID, there. The next bit is shell volume. And again, shell volume is listed right here. It's the one that we named earlier. Shell volume. That is our complete equation. The only thing I don't like about this is that when I actually click on compute, we're going to get this volume in cubic millimeters. We want liters. So let's just divide it by mil. So now we're going to do this and compute it and actually see what is what our volume is going to be. Bear with me a minute. I did just get a note from someone saying that they are having some audio issues. Give me 1 second here. I think we're all set now. I'm sorry. If there are any more issues, again, just type it in there and we'll get that to you. Okay, so I'm going to go ahead and run the result. And basically what it's saying is that, yes, it's possible. If I expand local parameters, we're going to see that we have a new parameter now. It's called fluid. Fluid underscore volume. That's basically what we created up here. So I will click on OK. And you can see in the model tree that we already have a feature that's been created there, so just accept that. And what it's telling us that in this current configuration, the volume of the void is going to be 7.7 liters, which is too much. We need to have it at 7 liters. So at this point here, we are actually going to run a sensitivity analysis. Okay? This is where behavioral modeling comes into play. We're going to run the analysis, and let us name this what we're going to do here is actually tell it, all right, so we need a dimension. We need some sort of value to change. So I'm going to select this D2 unit right there. It happens to be 280 something. So I'm going to give it a range. Make it 200 to 300 units. And the parameter to plot is going to be our fluid volume. That's what it's going to use as the equation. That's the equation it's going to use to figure out what the volume is. So hit OK like that. There is our fluid volume to plot right there. Before I go, under Options, I do want to animate the model, but we are actually going to see a graphic here as soon as we get into it. Okay. So what's happening here is as that D2 dimension changes from 200 all the way to 300, we can see that the volume of the cylinder of the container is going to change as well. So if we want it to be 7 liters, we can see that the D2 value needs to be 280 millimeters. Okay. So let's just think about this for a moment. How long would this have taken if we had to actually go in there and change the value increment by increment? Eventually we would have gotten it, but that's a lot of work. This took a couple of minutes and it's all set up. Okay, so that is example 1. I'm going to move on now and close this one up and run another analysis. At this point, what we're going to do is we want to see what the center of gravity on this crankshaft is prior to assembly. And of course, the crankshaft needs to be balanced. We need to ensure that the weight of this top area here is going to be equal to the weight of the bottom area. If there isn't, of course, there's going to be a lot of vibration, a lot of wear, a lot of problems. So let's figure out what the center of gravity is. Again, we're going to go under our Analysis tab, go to Mass Properties. Let's just go ahead and select. Let's just go ahead and analysis. You'll see that the density is 0. This is just a blank part, but of course it's not going to change where the CG is going to be. It looks like it's in the middle right now until, of course, we come over here and show it from the side. And we see the center of gravity in comparison to the default coordinate system is way out of whack. So before I close this, I do want to actually convert this to a feature. Call it mass. I'm just going to use what's there already. And complete that. Actually, before we do that, as well, actually turn the visibility on. Now if I show my coordinate systems, we are going to see the coordinate system for the center of gravity. Now we have to figure out is what is the distance between the y on the coordinate system of the center of gravity versus the axis of this shaft. So that's pretty simple. It's just a distance. Measure distance. Let's select the coordinate system, turn on our axis display, press Control and select this axis here. Under results, we're going to see that the value is 0.35 inches, so it's pretty far off. We need to make that 0. There, let's see a little better. And now we are also going to actually save this and call it COG, center of gravity. Okay. And what is it? I'll tidy things up and get rid of our axis display. So this is what we see here. We have our center of gravity measure and our mass properties of the part. The next thing we have to do is actually see if it's possible to get the center of gravity and the distance to equal 0. So what we're going to do is actually conduct a feasibility study. That is this icon up here. So let's conduct a feasibility study. It is going to default to optimization, but we want to look at feasibility. Now, before I talk about what those two are, just note that feasibility is just going to run one simple calculation to see if it looks like there's going to be some change in the equation. Optimization, on the other hand, is going to run the entire equation depending on the values that you give it to, and that could take a couple of seconds, it could take a couple of hours. That's why we want to make sure that it's possible first. So under our parameters, what I actually want to do, actually, let's give it a name before I forget that. Let's call it add to here VOG measure to our parameters. I want the center of gravity to equal 0. Okay, and it's going to appear in here. The next thing I'm going to do is go into my design variables and give it some dimensions to actually vary. The dimensions that I actually wanted to vary are the width of this lower lobe here. I want to set the height from the center point to the bottom of the lower lobe, as well as this radius of 8, which happens to be this entire rounded surface. Let's give it some minimum and maximum values. Start with a minimum of 2 and a maximum of 6. So 2 again, let's go 5 there. And lastly, we'll start with 6, 6, and we'll go. Okay, so we've added these values here. And we are going to go ahead. This, and what I want to note for a moment is, remember, this is just feasibility. Is this possible? Down here in the bottom left, in our play area, we're going to see if it actually can do this. Compute. It'll run through an analysis very, very quickly and say, yes, a feasible solution has been found. But that's great. You know, it did change some values to 2.18, 7.99, 3.62. That's great. I'm glad to see that it is possible, but I actually want to give it a, is this the optimal feature? So I'm going to undo that and close it. What I actually want to do now is give it another value. I want to actually tell it that I not only want this to be as small as possible, but there are some additional parameters here. I need to make sure that the minimum material thickness between this lobe and this lobe stays at a certain minimum. Otherwise, we're going to have some sort of issue maybe with structural problems. So we have to make sure that we do have a minimum width. What we're going to do now is go under, again, Measure, create a distance measurement, and I'm going to select this edge and this edge here, and our distance is going to be 1.5 inches between that edge and that edge. Let's actually call it something here. Let's save this as a feature, and we're going to call it material measure. Everything that all these names that I'm giving to these features, we are going to use later. So I'm going to close that now. At which point I have to run the feasibility and optimization tool once again. Now, of course, I'm going to add one more parameter. So add, we're going to add the one that we just created, which is material measure, which is right here, distance, material measure, and we want to make sure that it is less than equal to 0.25. Add that. Now we have 2 parameters to satisfy. And again, very quickly, let us just run feasibility. Is it even possible? So it did change some values, see that they are different from earlier, and it says that yes, a solution has been found. I'm going to undo that once again. Now what I want to do is go under optimization and say, okay, I actually want to see what the optimal weight is. I'm sorry, what the optimal dimensions are, not just local mins and maxes. And what I mean by that is what the feasibility analysis is actually doing. It's taking us back to calculus, all right? It's starting at this point here and going, okay, is there a minimum value? And the first one it finds is this minimum value here. Oh, that one there, actually. That's one of the maximum values. So then it's going to find a minimum value. And yes, that's great. This is a minimum value. This is a maximum value. But is it the true minimum? Maybe it's this maximum. Maybe it's that minimum. That's what the optimization study is going to do, is actually show us which is the true minimum material thickness that we want to work with. So I'm going to put this over here. We are going to see this actually happen in real time. Go to Options and Preferences, make sure that we graph our goal, and also ensure that the model is animated. Again, this just kind of makes life a little bit easier. Also under here, we're going to see that there is a maximum iteration of 50, as well as convergence of 0.5%, which basically means it's going to be accurate. The center of gravity is going to be aligned to that axis up to 0.5%. That's pretty close. And you obviously can't come in here and change it. So let's go ahead and compute this and see what happens. So as it moves forward, we're going to see that that these values have changed. Normally I run about 50 of these, but it took a few seconds to do 4. And again, just in terms of everybody's time, I didn't want to spend 10 minutes doing this. The values have changed, and we can see that they've changed and come to a stop change because the slope has gone from very great to slight to completely zero. So when the slope levels out, that's when it knows it's hit the true low point. At this point, we have actually completed our optimization study. This feature now exists, and we have the ability to export this into an outside tool, or in fact just open up Creo Simulate and now run simulation analysis using our behavioral modeling results. Okay, that said, let's go ahead and move on to the last bit of our presentation. I'm going to double check real fast and make sure that there aren't any questions. Looks like we're all clear. So what did we actually talk about here? We started off with a volumetric analysis. Okay, and in order to do that, we had to take the volume of the solid object, subtract that from the volume of the shelled object, and then we were going to get the final volume. That would then allow us to conduct a sensitivity analysis going over a range of values to figure out what the optimum height is of the bottle in order to get a maximum amount of fluid of 7 liters. So again, 7 liters simply says that we need 280 units to actually get that volume in there. And remember, we are omitting that nipple on top because that is not going to be filled with fluid. In terms of feasibility and optimization, our scenario was a crankshaft and seeing if the center of gravity was going to be along the axis of the crankshaft. So what did we do? We figured out where the center of gravity was. Then we conducted an analysis to see what the distance between the axis and the center of gravity was, and then applied that to a optimization study to further see what the optimum values of not only the width of the lobes, but the radius of the base lobe and the height from the center, from the axis to the bottom lobe was going to be. Lastly, we ran the calculation, and yes, you can see here that I have kind of spent some, given Creo a little more time here to find the results. We did have about 50 iterations. Actually, that was about 17 iterations, and we basically focused on this dimension here, this dimension here on the bottom, as well as the overall radius of the base. And again, just because I selected these does not mean that I could not have selected more or spent more time in the model. Behavioral modeling is going to allow you to optimize anything. You want to figure out a way to minimize clearances within some sort of a feature, minimize surface area, maximize weight savings, minimize weight. It's all going to be within behavioral modeling. And again, this is all integrated with all of Creo Parametrics design tools. I only have scratched the surface, but it's just an idea of some of the features that behavioral modeling actually apply to you. At this point here, I do want to open the floor for some questions. Okay, I do have one question so far here. We'll flip the window here a little more. Okay, the question is, how do you know what the how do you know what the feature IDs are? That's an excellent question. Let's go back to that model. So, all right, so the equation, we have one side vol, so 1_side_volume. And feature ID, again, this is just a consistent naming convention in Creo parametric. Bottle volume was simply what I named the feature. Shell volume is what I named the feature. One side vol happens to be the name of the parameter. Just bear with me a minute and I'll get that model back. So our bottle volume here, I'm going to right-click on that and edit the definition. The parameter, the minute you select a plane to focus the volume on, it's going to change the ability, or it's going to change the area that the volume is going to be calculated. This is automatically going to give it a parameter of one-sided volume. It just so happens that I changed it earlier to 1_side_vol. Therefore, I simply had to make sure that the next one, which is my shell analysis, had the same parameter. That's it. Once I know this, I can say, okay, I need to know the volume from parameter, one side volume, but because it's a parameter, there can be multiple things referenced, and I wanted to reference feature ID, bottle volume. Hope that clears things up a little bit. Any other questions? All right, well, I'd like to thank you all for attending. This Power Hour will be uploaded within the next couple of weeks, so you are going to be able to go back over it. And definitely let us know if you have any questions. My phone number is there on the slide. Thank you very much, and have a nice weekend.